Poisson bracket and equation of motion. So let us define a function f, which is a function of qi, pi and t. So this is the similar to Hamiltonian. Example is h is equal to h of qi, pi and t. Now now if you differentiate this, df will be equal to dou f by dou q into dq plus dou f by dou p into dp plus dou f by dou t, because it is with respect to time, into dt. Now since there are different coordinates, that is qi, pi, we have to put I here, so it's dqi, this is dpi, and here we need not put I because time is independent. Now since we have put I for each different quantities, there is a need of summation over I, and this summation is valid up to this particular point. So this is what we get after differentiating. Now what about df by dt? We are finding out how the quantity f is changing with respect to time. So now we get sum over I dou f by dou qi dqi divided by dt plus dou f by dou pi into dpi by dt plus dou f by dou t. Now here again, so dqi by dt, so that is dqi by dt equal to qi dot, and dpi by dt is pi dot, right? And according to Hamiltonian equation of motion, we know that qi dot is equal to dou h by dou p I, and pi dot equal to minus dou h by dou q. Now we need to substitute dqi by dt to p, that is dqi by dt, that is qi dot, that is dou h by dou pi, and pi dot with minus dou h by dou k dot. Now this becomes sum over I dou f by dou qi dqi by dt is dou h by dou pi, dou h by dou pi minus, that is because of this minus here, dou h by dou q, that is dou f by dou pi times dou h by dou qi plus dou f by dou t. Now that is equal to df by dt. Now defining this particular quantity, this is just like commutator a comma b equal to ab minus ba. So this is a, this is b, this is again b, a. Okay, fine. Yeah. Now df by dt we can write it as in classical mechanics, that is in Hamiltonian, df by dt, the total time derivative of f, is equal to, this particular quantity is nothing but f comma h, this is Poisson bracket f comma h, you can write here Poisson bracket plus dou f, partial derivative of f with respect to time. Now in quantum mechanics we write the change of the function f with respect to so this is total time derivative df by dt, where f is the operator, is equal to 1 divided by I h cross f comma h, this is quantum commutator, plus dou f by dou t. So in general you can write the Poisson bracket of Poisson bracket is nothing but, that means in classical mechanics is nothing but in quantum commutator, that is the quantum commutator divided by IH cross. So whatever we need to find out the Poisson bracket, just put it into the quantum commutator and divided by IH cross, gives you the classical time derivative of a function. Before going to the problems based on Poisson bracket, here are some properties of commutators, quantum commutators. A comma b commutator is minus b comma a and a comma b plus c plus d plus etc. if it is going like that. So you have, that is equal to a comma b commutator plus a comma c commutator plus a comma d commutator etc. Now a comma b c commutator is a comma b c plus b a comma c. Okay, so a comma b commutator whole dagger is b dagger comma a dagger commutator. Now a comma constant commutator of a comma some constant is 0, commutator of a comma a is again 0, so commutator of a comma f of a is again 0. Now a comma b comma c plus b comma c comma a plus c comma a comma b, all in commutator, is equal to 0. This is called Jacobian identity. Now these all are true for Poisson brackets also. Okay. Properties x comma px. So here you will have q comma p commutator equal to q comma p quantum commutator by IH cross. So here you will get x comma px. So x is nothing but position, px is momentum along px x, so which means this is qp, so qi pi, so qp by IH cross, that is nothing but 1, because here you will have IH cross divided by IH cross, that's equal to 1. So px comma x minus IH cross, x comma py, because they are in different direction, 0, a comma f of b, so that is nothing but a comma b into d by db of f of b, a comma function of b. Now here it is x square comma px square is 2IH cross xpx minus pxx. Consider the Lagrangian of the simple pendulum. Lagrangian for simple pendulum. So L is equal to half m L square theta dot square minus mgl into 1 minus cos theta. Now we are asked to find the Poisson bracket of theta dot comma p theta, then theta comma p theta dot, and theta dot p theta dot. Now theta dot comma p theta, let us see how we can write this. Now the Hamiltonian for the simple pendulum can be written as p theta square by 2m L squared plus mgl into 1 minus cos theta. So this is how we can write the Hamiltonian. Now theta dot is equal to dou h by dou p theta. That gives you p theta by dou p theta is p theta, 2 gets cancelled, so p theta by ml square is nothing but theta dot, and we need theta dot comma p theta. So theta dot is p theta by ml square comma p theta. So commutator for p theta comma p theta, that's nothing but 1 by ml squared p theta comma p theta. Now that's equal to 0. So that comes under the property pi comma pi commutator equal to 0. Coming to the theta comma p theta dot, now again the Hamiltonian is equal to p theta square by 2m L squared plus mgl into 1 minus cos theta. So p theta dot is given by p theta dot is equal to minus dou h by dou theta. So dou h by dou theta is the first term doesn't contain theta, so this becomes minus cos theta minus sin theta, so mgl sin theta. So with the minus sign, mgl sin theta. Now theta comma p theta dot, we can write it as theta comma p theta dot is nothing but minus mgl sin theta. Now this comes under the property theta comma f of theta times, now what is the function of theta? That is sin theta. So mgl will be outside, so that's, we can write it as 0. So this is something like this: a comma f of a commutator. So this gives us the product 0. Now coming to theta dot comma p theta dot, we have theta dot formula, that is theta dot equal to p theta by ml squared comma p theta dot s minus mgl sine theta. So this commutator. Now take out the constant minus mgl divided by ml squared into p theta comma sine theta. So p theta comma sine theta, so this is nothing but a comma f of b is equal to a comma b into f dash of b. So that gives us minus mgl divided by ml squared p theta comma theta. Sin theta differentiation is nothing but cos theta. So here we have get cancelled, ll get cancelled, so g by l with a minus sign into p theta comma theta is again minus 1 times cos theta. So that's equal to g cos theta by l. So this is the, here we get the answer. Theta comma p theta dot is g by l cos theta. For the simple harmonic oscillator, the Lagrangian of the system is defined by L is equal to q dot square by 2 plus q square by 2. Now if A is equal to p plus iq by root 2 and B is equal to q minus ip by root 2, find a comma h and b comma h. Poisson bracket a comma h and b comma h. Now from here we can write that the Hamiltonian h is equal to sum over I qi pi dot this is sum over I qi dot pi minus L. So here it is q dot by q dot and pi so here pi is equal to dou L by dou q I dot so dou q dot, so it's we can write it as q dot p minus L. So p is equal to dou L by dou q dot, that's equal to q dot, and So now we know that this is P equal to Q dot, and this gives us Q dot into, so Q dot equal to P, so that becomes P square minus L. What is L? L is Q dot square by 2 minus Q square by 2, and this gives us Q dot square is nothing but P square by 2, so that means P square by 2 minus Q square by 2. So H is the Hamiltonian, which is given by P square by 2 minus Q square by 2. Now we need to find A comma H. So for that we have P plus I Q by root 2 comma that are P square minus Q square by 2, that is the Hamiltonian. So this can be written as 1 by 2 root 2, and within the bracket P plus IQ, that is, let us take this one first, P plus IQ comma P square Poisson bracket minus P plus IQ comma Q square. So this gives us P plus IQ, P gets cancelled, so IQ comma P square, that is 2P, P comma Q comma P is 1, so let's in detail write this, 1 by 2 root 2 into this we can write it as P comma P squared plus IQ comma P squared minus P comma Q squared minus IQ comma Q squared. Now you can see here the P comma P square is 0, IQ comma Q square is 0, both A and B are same, so A comma A is 0, so what is left with is IQ comma P square and P comma Q square. So IQ comma P square will give you 2IP, because Q comma P is 1, so differentiation of P square is 2P, so it is 2PI, and here you have P comma Q square, which gives you P comma Q is 1 minus 1, and Q square differentiation is 2Q. So writing this once again, 1 by 2 root 2 times P comma Q squared and P comma Q squared and minus P comma squared plus IQ comma P squared. So this gives us 1 by 2 root 2. The first term gives 2q, and here I 2p, so I 2p. This is bringing this 2 root 2 inside, 2 gets cancelled, q plus ip by root 2, so that is q plus ip by root 2. Then now the second one is b comma h, so that gives us q minus ip by root 2 comma p square minus q square by root 2. So here we will do it in more simpler way. Q will not go with p square, which gives you 0, so q goes with p square here, so q p square gives you 2qp, so that is q comma p, that is 1, and 2p remains, so that's 2p, and q with the q square gives you 0, and ip with this ip with p square gives you 0, and ip with the minus q square, so I minus ip, so that let us write down that, plus minus ip comma minus q squared, so that's equal to 2p plus minus ip, so that is minus I p comma, so minus and minus, that gives the plus sign, so p comma q square, so that's 2p plus I p comma q is minus 1, q square is 2q, so minus 2q. So here we have 1 by root 2, and sorry, this is, I think it's 2 p square q square by this is 2, so it gives us 1 by 2 root 2 into 2p minus I2q, so 2p minus I2q, this gives us, bring this to the denominator, that means p minus iq by root 2, and here we have got q minus ip, and now from here this we can write it as I times qi, and that is iq with the minus sign, and plus p by root 2, so this is nothing but p minus iq, so that is what is a is equal to p plus iq by root 2. Now what is a star? A star is equal to p minus iq, that is complex conjugate, by root 2, and this is a comma h. A comma h is nothing but I, and this term is a star, so a comma h is a star, while we have got this as b comma h. This is b comma h equal to this one, and taking the I outside, let's see what happens. I, when you take out, that is minus ip plus q divided by root 2. So we need in terms of b, so b is what is b? B is equal to q minus ip by root 2. So put a minus sign over here, so this becomes plus and this is minus, so q minus ip by root 2, so that's equal to minus ib. So b comma h is minus ib, and a comma h is ia star represent the complex conjugate. Hamiltonian for relativistic particle. This is Hamiltonian is nothing but mc square. And what is m? M is equal to m naught by under root 1 minus v square by c square. And for the relativistic particle, m naught is the rest mass and v is the velocity at which the particle is moving, c is the speed of light, and this is also we can write it as gamma m naught, and this is the Hamiltonian for that. Now coming to the charged particle in electric and magnetic field. So charged particle in electric and magnetic field, we are going to write what is the Hamiltonian. In the first phase we will deal with the non-relativistic particle. In the non-relativistic case, the charged particle, let the charge to be q and a be the vector potential, then phi the scalar potential, then we can write the Hamiltonian H is equal to P minus QA by 2m, this is whole squared, plus Q times phi. So this is the non-relativistic Hamiltonian for charged particle in electric field and magnetic field. Now coming to the relativistic particle. Relativistic case, Hamiltonian is given as root of P minus QA whole square C square plus m naught C power 4 and it's m naught square C power 4 plus Q phi. So this is the relativistic case, and for relativistic in the case of neutral particle, we can also write this as p square C square plus m naught square C power 4 all to the power 1 by 2. This is also equal to mc square, that's equal to Hamiltonian. So these are the Hamiltonian for relativistic as well as charged particle in electric and magnetic field. This is another topic here, equation of motion. Now we have derived the Poisson bracket from the equation of motion earlier, and df by dt. So this is the derivative of f with time, which is equal to f, okay, let's write here capital F. So f comma h plus dou f by dou t. So this is the equation of motion. Now when can we say that f is constant of motion? So constant of motion. Now when can we say that f is constant of motion? This is said, or f is conserved. When we say this is constant of motion, it also means it is conserved. When we can say that whether f is constant of motion or conserved, then this can be said when df by dt is equal to 0. Now for this there are three conditions. Either f comma h should be equal to 0. Sorry, two conditions. Either f comma h and dou f by dou t together equal to 0, and now there is another, or you can say f comma h is equal to minus of dou f by dou t. So these, in either of these conditions we can say that the f is constant of motion. Now just for an example, we will take the Hamiltonian of some system. H is equal to q1 p1 minus q2 p2 minus omega q1 squared minus mu q2 squared. So this is the given Hamiltonian, and the function f is given as q1 e to the power minus t. So now this is the function. With respect to this Hamiltonian, we have to understand whether it is constant of motion or not. That means we should know first f comma h. So f comma h is q1 e to the power minus t comma q1. Wherever there is q1, we can put it that q1 p1 now here q1 p1. Now q2 we do not require because it's a different term. Now here omega q1 squared. Now omega q1 squared means it consists of q1, so q1 with q1 will go to 0. So q1 e to the power minus t and q1 p1. So this is what we need. This gives us q1, and q1 you can take it out, q1 e to the power minus t, q1 comma p1 is 1. So q1 e to the power minus t is f comma h, and now we need to find out what is minus dou f by dou t, dou f by dou t. So that's equal to q1 e to the power minus t, and with a minus sign, derivative of e to the power minus t is minus q1 e to the power minus t. Now look at this. F comma h is q1 e to the power minus t, and dou f by dou t is minus q1 e to the power minus t. So this tells us that f comma h plus dou f by dou t equal to 0. So this is consists from the second condition, that this is equal to 0. So f is constant of motion. Now specifically this particular quantity f is equal to q1 e to the power minus t is constant of motion.